sometimes a group can lean over so much that it falls over and it moves over to that other carbon. Carbocation rearrangement is a concept that sometimes just always feels out of reach for students. Students understand what carbocation rearrangement is, but they seem to have trouble doing carbocation rearrangement on a consistent basis. This is a concept where I don't really have a 3-step foolproof plan. I have a 1-step foolproof plan. Always check for carbocation rearrangement. Always. Every single time. Every time you draw a carbocation, when you're drawing a molecule, if you're going to draw a carbocation, it needs to be Pavlovian. Every time you draw a carbocation, you need to think, can it rearrange? Carbocation rearrangement, carbocation rearrangement, carbocation rearrangement. Can it rearrange? Always. Always check for carbocation rearrangement. Most of the time, the carbocation won't rearrange, but those few times it does, you will be glad that you checked. I cannot tell you how frustrating it is as a student to get an exam back and see that you missed a point because you didn't do the carbocation rearrangement. Always check for carbocation rearrangement. Why do we do carbocation rearrangement? Very simple. Molecules will do anything they can to be as stable as possible. That's one of the guiding principles of chemistry. Molecules will do anything they can to be as stable as possible. All right. Molecules don't have agency, but molecules will do anything they can to be as stable as possible. One of the ways they can do that is carbocation rearrangement. How did that happen? A carbocation goes from a carbocation that is less stable to a carbocation that is more stable. It increases the stability of the carbocation. And if we increase the stability of the carbocation, we increase the stability of the entire molecule. To do carbocation rearrangement, then we have to remember our carbocation stability trend. This isn't a video about carbocation stability trends. I have a separate video that I've linked down below. But we have to know which carbocations are more stable than which other carbocations. Any carbocation can rearrange. The question is, will it become more stable after it rearranges? Not all carbocations rearrangements that can happen will happen. So the question, the way I like to pose the question is, we're sacrificing what carbocation to gain what other carbocation? So if we look at this example here, this carbocation is a secondary carbocation. Secondary carbocations, okay, it's fine, but it can rearrange. Will it rearrange? That's the question. We need to look on all possible directions to see if the carbocation can and will rearrange. If we look over on the right side, there is a hydrogen over here on the right side that could rearrange, a hydride shift. If we do that, there are 3 hydrogens on this carbon. If we rearrange one of these hydrogens, we'd be sacrificing a secondary carbocation to gain a new hypothetical primary carbocation. Can that happen? Sure, yeah, it can. It's mechanistically legal. Will it happen? No, not in this case, because a secondary carbocation is already more stable than a hypothetical primary carbocation. We're not going to sacrifice a secondary carbocation to gain a less stable primary carbocation. If we look on the other side, we have a hydride here, a hydrogen atom here, that could rearrange. Will it rearrange? If it rearranges, we would get a new tertiary carbocation. A tertiary carbocation is, yes, more stable than a secondary carbocation. We'd be sacrificing a secondary carbocation to gain a tertiary carbocation that is more stable. Yes, this carbocation will rearrange. So how does a carbocation rearrange? Carbocation rearrangement is kind of a natural extension of hyperconjugation. This isn't a video about hyperconjugation. I've got a separate video linked for that down below. But with hyperconjugation, recall that the neighboring groups around a carbocation are kind of leaning over a little bit, sharing some of their electron density with the carbocation to make the carbocation more stable. Well, sometimes a group can lean over so much that it falls over and it moves over to that other carbon. And if it moves over to that other carbon, it has rearranged from one carbon to another. That's how carbocation rearrangement works. We break the CH bond. This CH bond was leaning over, sharing some electron density with that carbocation. We break the CH bond, and this hydrogen moves over and forms a new bond with the carbocation. This is an example of a bouncing arrow. This isn't a video about bouncing arrows. I have another video about bouncing arrows down below. This says that we're breaking the carbon-hydrogen bond. Hydrogen is using those electrons to form a new bond with this carbon. The result of this carbocation rearrangement, then, is the carbon backbone stays the same, and we have lost the hydrogen on this tertiary carbon, and we have a new carbocation on this tertiary carbon. That hydrogen still exists. It's still on this carbon. There was already one hydrogen on this carbon, and it's still there as well. And we still have the 3 hydrogens on the carbon on the right. This is the result of the carbocation rearrangement. We sacrifice a secondary carbocation to gain a new, more stable tertiary carbocation. Hydride shift is by far the most common carbocation rearrangement that we see in organic chemistry, but an alkyl shift is also perfectly reasonable and happens fairly frequently. We need to be on the lookout for that as well. Again, sacrificing what to gain what? The current carbocation that we have is a secondary carbocation. We need to know the degree of substitution of the carbocation. This isn't a video about degree of substitution for atoms, but we have a separate video linked down below for that. If we're going to sacrifice the secondary carbocation, what would we gain as a result? If we rearrange on the left, we could move one of these hydrogens over as a hydride shift. We'd be sacrificing a secondary carbocation to gain a different secondary carbocation. We're not going to sacrifice a secondary carbocation for another different secondary carbocation. That doesn't make the molecule more stable. It makes it the same stable. There's nothing mechanistically illegal about it, but it's not going to happen because it doesn't make the whole molecule more stable. If we look over on the right side of the molecule, if we move one of these methyl groups over, we'd be sacrificing the secondary carbocation to gain, after the methyl group moves over, a new tertiary carbocation. It's not tertiary right now, but it would be tertiary after the rearrangement. And tertiary is more stable than secondary. So yes, we will sacrifice the secondary carbocation to gain the new tertiary carbocation. The reaction, the mechanism happens the same way. We break, in this case, the carbon-carbon bond, and it's the methyl group, the carbon atom, that rearranges to form the new carbon-carbon bond. Again, using that bouncing arrow. We do the carbocation rearrangement to shift the methyl group over one position. Now the methyl group is attached here to this carbon. It has left this carbon on the right. This carbon on the right is now a tertiary carbocation. It is now missing its electron. It is now a carbocation. We have rearranged the carbocation from a secondary carbocation to a more stable tertiary carbocation. The last kind of carbocation rearrangement we should look at is ring expansion. It's definitely the highest ninja level of all of the carbocation rearrangements. Let's take a look. We have a carbocation. Again, we need to identify its degree of substitution. This carbocation currently is secondary carbocation. We're not going to rearrange on the right. Hopefully we can see that by now. We'd have to sacrifice a secondary carbocation to gain a primary carbocation. That's not going to happen. Let's look at carbon number 3, though. If we do a rearrangement at carbon number 3, we have a couple of choices. We could break the carbon 3, carbon 7 bond and do an alkyl shift and move carbon 7 over to carbon 2. That would sacrifice a secondary carbocation to gain a tertiary carbocation. But what I want you to notice is this 4-atom ring. We call it a small strained ring. 3-atom rings, cyclopropanes, and 4-atom rings, cyclobutanes, are small strained rings. They're very unstable because of their ring strain. If we can make that ring more stable, that would make the whole molecule more stable, and molecules will do anything they can to be as stable as possible. So watch what happens. Instead of breaking the 3-7 bond, we're going to break the 3-6 bond. We're going to use the electrons, the electrons are going to stay with carbon 6, and we're going to form a new bond between carbon 6 and carbon 2. We're going to break the bond between carbon 6 and carbon 3, and form a new bond between carbon 6 and carbon 2. This is the ring expansion. This will sacrifice a secondary carbocation to gain a tertiary carbocation and make the ring bigger and more stable. How do we draw this next intermediate? I'm going to use what my friend James calls draw the ugly version first, and I've got a link down to his video down below if you want to give him a little bit of love. To draw the ugly version first, we play connect the dots. We leave all of the carbons in the same place. We give them all the same numbering, but we don't add any sticks yet. We don't add any bonds yet. So this would be all the dots for all the carbons in all the same place. We didn't do anything with the carbon 1, carbon 2 bond, so that bond stays the same. We didn't do anything with the 2-3 bond, that bond stays the same. We didn't do anything with 3-7 or 3-4 or 4-5 or 5-6, but this arrow says that we broke the 3-6 bond, so the 3-6 bond is broken. And this arrow says carbon 6 used those electrons to form a new bond with carbon 2. So that would look like this. No, that's not a very pretty version of the molecule. Nobody cares. Go ahead and draw it, so at least you get the carbons in the right place. Then we can redraw it as a prettier version later. When we break this bond, in order to break the 3-6 bond, we had to take the electrons away from carbon 3 so that carbon 6 could form a bond with carbon 2. We had to take the electrons away from carbon 3. So now carbon 3 is deficient electrons. It only has 3 bonds, no implied hydrogens. Carbon 3 is where the new carbocation will go. We had to take the electrons away from 3 to form the bond with 2. So carbon 3 is the new carbocation. This is a fine representation of the molecule. It's a little bit unusual though, so we'll redraw the molecule. These 3 lines means is equivalent to. So we'll redraw the molecule. So it looks like our ring now is 1, 2, 3, 4, 5 atoms big, a 5-atom ring, so a cyclopentane. We can redraw a cyclopentane, and it looks like those atoms are 2, 3, 4, 5, and 6. Carbon 3 is still attached to carbon 7, so we'll draw the carbon 3, carbon 7 bond. And carbon 2 is still attached to carbon 1, so we'll redraw the carbon 2, carbon 1 bond. The carbocation again is on 3. That's where we formed the new carbocation after the ring expansion. This is what this molecule will look like after the ring expansion. Definitely the highest ninja level of all the carbocation rearrangements, but it follows the same principles. We're sacrificing a less stable carbocation to gain a more stable tertiary carbocation. With these tools, you too can become a ninja with carbocation rearrangements. Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more.
As always, don't forget to like and subscribe.